we're going to look at oscillations that are objects moving back and forth, and particularly at a particular kind of oscillation called simple harmonic motion. First off, a more general term, periodic motion. Periodic motion is any motion that is repeated. So if you bounce a ball over and over and over again, that could be a periodic motion. If you are throwing a ball up against a wall over and over again, if you're, I don't know, jumping every 3 seconds, that would be periodic motion. A few pieces of terminology. Some you may have heard before. The period, which is capital T, is just the time for one cycle. So like I said, if you're jumping up and down every 3 seconds, then your period would be 3 seconds. And closely related to the period, also a useful measure is the frequency, which is letter F, and this is the number of cycles per second, and as such is the inverse of the period. And since it's 1 over seconds, the unit is inverse seconds, also known as Hertz, after a guy named Heinrich Hertz, who did a lot of work with radio waves, I believe. Yeah, but those are a couple of simple things related to periodic motion. Now, more specifically, for simple harmonic motion, which I will abbreviate SHM from this time forward, simple harmonic motion is defined as a periodic motion with a restorative force proportional to distance from equilibrium. Okay. So that means objects going back and forth, back and forth, back and forth, and there's some sort of equilibrium position, and the further away something gets from equilibrium, the greater the force pushing it back toward equilibrium. It's the term restorative. Perhaps the simplest, or the case that you might already know about, is like a mass on a spring. We know that spring force is equal to minus kx. This x telling us that the force is proportional to displacement from equilibrium, and the minus telling us that it's pushing back toward equilibrium. But this is the definition you'll apply to tell if motion is simple harmonic. So it should be fairly simple, to figure out if a type of periodic motion is simple harmonic. So for example, if you got two people and you're throwing a ball back and forth, well, that would not be simple harmonic, because while the ball is traveling through the air, there is no force, there's gravity pulling it down, but there is no restorative force acting on it. And you catch it and it stops, then you throw it back, you exert some force for a short amount of time, and then it's flying through the air again. The force is not proportional to distance from equilibrium. Right? As I said, the mass on a spring is a good example of simple harmonic motion. And for mass on a spring, you kind of have an idea of what happens. Say we've got a spring, mass, and it's resting on a frictionless surface. If we compress our spring, say this is equilibrium, if we compress our spring, now the force is going to be going this way. It'll be at rest initially. Then, as we get to equilibrium, force is 0, but we have a velocity still going this way. And as we get past equilibrium, now there's going to be a force pointing back toward the middle, and it'll slow down and stop. And once it reaches compress it, it forces this way, so it starts moving this way. At equilibrium, the net force is 0, but that still has the speed going to the right. And then as it gets past equilibrium, the force is pushing back toward equilibrium, so it does this kind of back and forth kind of motion. And if we were to draw that over time, it's going up this way, and then it comes back down, and then back and down, and back and down, and this looks kind of like a sine wave or cosine wave. And doing some calculus indicates that it is, in fact, a sine or cosine wave, because we know the F, the force, is minus kx. That's equal to mass times acceleration, which tells us that acceleration is minus k over m times x. Now, this is what the case for a mass on a spring. In general, for a simple harmonic motion, the acceleration is going to be some constant, minus some constant times x. Acceleration as a function of time is the second derivative of position. This is some constant times x. Well, what second derivative is itself with a minus sign, and that's a sine or a cosine function, because we know d by dx of cosine t, cosine of some constant times t, is going to be minus that constant times sine constant t, or d by dt, sorry. And if we go d by dt of that, the derivative of sine of negative sine is negative cosine, and then the chain rule pops out another factor of c. And so, we have some constant times our original function. And so that tells us it's going to be a sine or a cosine function. Typically, with simple harmonic motion, what happens is that we stretch or compress the spring, and so we have some initial position, and our initial velocity is 0. And if our initial position is some value, a sine function would start at equilibrium, whereas a cosine function would start at a maximum. So generally we say our position as a function of time is a cosine function. And then what is the period of this cosine function? Well, it's just the period of the oscillation. And we know from, well, you may not remember from trigonometry, but what goes in here is 2 pi over the period. So that's what goes inside our cosine. That's how we get a period of t for our cosine function. And then out here we have the amplitude, or the maximum displacement from equilibrium. We call that A. A stands for amplitude. So this is our position as a function of time for any simple harmonic motion. So I use the mass on a spring as an example to kind of show you how this works, but this is a general result that applies for every simple harmonic, for all kinds of simple harmonic motion. Now, from our rotational kinematics, this 2 pi over period, we give another name for, that's omega. In the case of rotational motion, we call it angular speed. In the case of simple harmonic motion, it's closely related, and I'll explain that a little bit more, but we call it angular frequency. Okay. So this can also be written as a cosine omega t.